First of all, I've been enjoying the seminar series over the last couple of weeks. We've had a lot of fascinating talks on varied subjects. And just to give a brief introduction about me, I'm a material scientist and I work on trying to simulate how materials behave in real life. And when the faculty seminar series came up, I was thinking of presenting on a topic that's really fascinating, not just for me personally, but I think everyone ought to know about several of these fascinating properties that glasses show. So the title of my topic is glasses, and hopefully by the end of the talk, I'm going to convince you why they are the original super cool materials. So when I thought of a topic to present, I did a brief survey of what are some of the technologically important materials out there. And interestingly enough, if I do a simple Google Scholar search for the number of articles on various materials, glass easily tops this list with about 57 million hits in Google Scholar. And you can compare that with other equally important, arguably, materials like steel, concrete, silicon, etc. But given the extensive use of glass, not just in present times, but from prehistoric times, I think combined with the fascinating properties that these glasses exhibit, they definitely lay their stake in one of the hottest areas of materials research, and not least a super cool material. So I think the best lens to view glasses from, pun unintended, is by looking at a very brief history of how these materials came about in present day use. So as we all know, it's one of the earliest materials to be used. I'm going to show you how it was used in prehistoric times, where people made various tools out of it. But what's really fascinating at a personal level is the amount of technological marvel that's gone in engineering these materials, right through medieval times and modern and contemporary history. So if you look at the earliest known history of usage of glasses, it's very fascinating to see that even about 1.5 million years ago, that's long, long ago, I don't know if anyone can claim any other material from that age, people were using glasses as natural materials. So obsidian is a natural volcanic glass. So this was formed when the hot molten lava essentially solidified as a function of time and at ambient conditions. So this was, as you can see, a very fascinating material. It was very strong, and it found its use in making small weapons. For instance, this figure here shows an arrowhead that's made of obsidian. Several other natural glass formers were also known. So all these were vitrified glasses from natural instances. For instance, when a lightning struck sand, as we know, it rapidly transforms the sand into a vitrified glass that's called as fulgurite. And again, this was used as prehistoric weapons. So it's interesting to see that there can be an entire mountain or a hillock made of these fascinating glasses. So going further down the history, or going forward, even as late as about 3500 BC, people started developing these technologies where they could start processing glass by making small contributions in additions to make these glasses, and it found extensive use in making jewelry and decorative items. For instance, there's documented history of glass beads from as long as 3500 BC in Egypt and Mesopotamia. One such glass jar is shown in the picture here. So now if we skip forward, not much happened from prehistoric times to about the medieval period that I've mentioned here. But the real use of glasses, as we all know, came in designing various pieces of decorative items. For instance, cups and jars were the rage back in the days, and people used this as a status symbol. One of the Roman cups from the early medieval period is shown here. What's really fascinating is some of these glasses began to be shaped into the spectacles that we know of today. So again, people in Italy and France, they were pioneers in discovering the optical properties of glass, and they were successful in processing glass and also shaping it into the applications that we see in the present times. One of the unmissable use of glass is in exquisite window panes that you see in this picture on the right. So this is from the famous Chartres Cathedral in France from the 13th century. So you can see the amount of technology that's being evident in these pictures. So you don't necessarily need to just control the glass processing, but you can also fine tune how the glasses appear by various chemical additions. So now going forward to modern contemporary research, it's not an understatement if we say that there's a lot of research that's happened, and we know properties of glasses and processing conditions that we can employ to engineer glasses with far superior properties than was ever possible in the medieval times. So the biggest and the most ubiquitous example that comes into my mind is the modern spectacles. Right? So these glasses, as we know, traditionally they were made of the silica glasses, and further research enabled people to create glasses out of plastics. So I'll show you how plastics are also glasses. And these specific glasses had superior properties. They could show photochromatic effects. They were also amenable for various coatings that imparted anti-glare, anti-scratch properties. One of the technological marvels that we can see is the electronic displays in mobile phones and TVs. So what I've shown here on the left is the iconic Gorilla Glass that was pioneered by Corning about 10-15 years ago. And these glasses are virtually indestructible. You might probably need to take a hammer and then bang it a few times to actually break this displays. So that goes on to show how by various technological advancements, we can really optimize these glass structures to get far superior properties than was ever possible. And of course, we have several applications in high strength, in places where we need very high strength. And this is clearly evident in various construction sites that we see. The picture that I had shown in the first slide was the Louvre Museum, of course. And it's not surprising that they've also been used as shields in aircrafts and automobile industry. Okay, so that's a brief overview of the history of glasses. Now let's try to see and delve a bit deeper into what exactly are glasses. How can we think about the structure of glasses, what properties they show, and eventually I will move forward to describing what are the various processing conditions that we can employ to get these fascinating properties. Okay, so glasses seemingly are very simple, right? So we've seen glasses at various places. So these are some solids, or as we'll see later, is it really a solid or not, that we'll come to see. But although it's seemingly simple, it's yet to be fully understood. And that is represented by this famous New York Times article that you see on the right. And the title goes as "The Nature of Glass Remains Anything But Clear." So there's a lot of research that's been happening over the last couple of decades, but some of these concepts of glass formation, how do you understand the physics of glass, has perplexed scientists even now, and it still remains to be a very rapidly evolving field. So here we'll see a few important questions. In particular, we'll see how one can characterize a glass. Okay? What is its structure, and what are some basic rules for glass formation? And I think this beautiful quote by Philip Anderson, a Nobel laureate, he made this quote in 1995. And he says that the deepest and most interesting unsolved problem in solid state theory is probably the theory of nature of glass transition. And this could be the next breakthrough in the coming decade. So now you might ask, since we are about a couple of decades from this statement, is this really true? Is there a breakthrough in the glass literature that basically explains what glass transition is? And the answer is, according to most scientists, no. There are still a lot of unsolved problems in solid state theory and condensed matter physics that people are still trying to grapple with. So if you look at the basic definition of a glass, Now going into a bit of material science, the definition goes like this. And there are a lot of alternate definitions, but equivalent definitions. But the definition I like most is what I've shown here. So a glass is a non-equilibrium, supercooled, non-crystalline condensed state of matter that exhibits a glass transition. Now let's take a few moments to break down what each of these mean. Okay. So the first concept that I would like to highlight is what is meaning of non-equilibrium. So if you go back to our preliminary thermodynamics, any process can be broken down as either an equilibrium process or a non-equilibrium process. So equilibrium process is one where at any point of time during this process, you're always in equilibrium, meaning when you take a step in the forward direction, you can come back in the reverse direction. Okay? So this is a very simple picture for this is basically the piston cylinder assembly where you can pick up one grain of sand at a time and control the height of the piston accordingly. Okay? So naturally, an equilibrium process is a very slow one. By very nature, you can interchange between the forward and the reverse direction. So glass is clearly not an equilibrium structure. In fact, it is a structure that's formed by rapidly cooling the liquid. Okay? And that's what we mean by supercooling, where the word super basically indicates that you need a reference state below which you need to cool the glass to. Okay? So what we're talking about again, to reiterate, we have a liquid structure and we want to create a glass out of it. The way we do it is by supercooling the liquid, meaning we cool the liquid below the melting point of the liquid. And what this does is essentially it traps all the atoms in a metastable structure. So I know there are a few words that may not be familiar with non-material science folks. So what do we mean by a metastable structure? So if you look at this graph, a very simple schematic on the right, so this plots the energy of a particular configuration or a material, to be more simplistic, as a function of certain coordinate system. That's the x-axis here. So you can see two small troughs in this figure. The trough that's labeled as number 3 is a much more stable trough, right? If you, for instance, place a ball in the trough 3, then it's almost impossible for it to move back to trough 1 without an external stimulus on the ball. Whereas if you consider the trough that's labeled 1, by just giving a small force or small perturbation, it's possible to make the ball tumble and go to the more stable state, which is the state 3. So in condensed matter physics, whenever we say a system or a material has lower energy, we mean that it's more stable. Okay. So glasses are rapidly cooled. They are metastable, meaning they're not in their true stable form. And we'll see in a moment what the true stable form is. But essentially, it's a metastable structure. And given enough time, the glass will eventually try to form a more stable structure. Okay. So with that in mind, one of the earliest questions that plagued the scientist's mind was to, how do you characterize a glass structure? Okay. And we seek help from Bragg's law of diffraction. So Bragg's law is highlighted here. So most of us know from physics that whenever there's a periodic arrangement of atoms, in this case, there are two planes of atoms shown by the blue circles. And whenever there's an incident light on this material, these atomic planes can diffract light. Okay. So what we mean by that is when these parallel beams of light undergo constructive interference, they will basically diffract light. Okay. And there's a specific angular relation that takes the material dimension into account, namely the periodicity, that's the atomic spacing d, and the angle of incidence at which this this light beam interacts with this material. And lambda here is the wavelength of the incident light. Okay. And the interesting thing that people found is when they characterized X-ray diffraction of these glassy materials. I'm showing one such example where we have a neodymium aluminum oxide glass and an equivalent crystal that can be formed from this material. We see that the crystal exhibits very sharp peaks, and these profiles are very well distributed at specific 2 theta degrees, 2 theta angles. All right. And if you look at the glass on the other hand, it obviously lacks this periodic order, the information that's captured in this periodic order. So that gives the basic hint that glasses do not have any long-range periodicity that crystals exhibit. What is very interesting is one of the earliest theories that was propounded to explain glass structure. What people thought was glasses were basically made of very, very tiny crystals that could not be seen with the naked eye, of course, but also that regular crystals exist over multiple unit cell spacings along the X, Y, and Z directions. They are bulk crystals in that sense, and they can be several thousand or millions of atomic planes that represent this crystal structure. What people thought was the glass structure was essentially something like a microcrystal, meaning all the glass crystals were very, very small, but they still had some crystalline order, meaning a periodic repetition of atoms. And it took a lot of time for people to basically look at the X-ray diffraction pattern and try to back calculate what the atomic spacing should be for this glass theory to hold. Okay, and this spacing that you see, right, the distance between the profiles of this peak, this came out to be of the order of just one atomic plane, meaning the order in glass is actually very, very tiny. It just shows a very simple short range order, and there's complete lack of long range order. And that's clearly seen in this figure on the right. So this is a diamond crystal structure. The one on the right side of this figure is a regular crystal structure, which has this nice periodic arrangement of atoms. And on the left, you see there's complete lack of long range order. Okay, but what's very interesting is the glasses still show short range order. And this is seen from this XRD peak that's shown here. So in some sense, to basically recap what glass is, so it's a very, very ambiguous topic, right? Some people might call it a solid or a crystal. Some people might call it a solid because glass, as we all see, is solid. We can hold it in our hand, and for all practical purposes, it behaves like a solid. But on the other hand, if you look at the structure, it actually resembles a liquid in the sense that it doesn't have any long range order. So the way I would like to think about it is this classical physics explanation of is an electron, whether a particle is an electron, a particle, or a wave. So something equivalent in condensed matter physics is glass a solid or a liquid? The short answer is it's both. Okay, and following on, there was this pioneering theory from Zachariasen, and Zachariasen propounded this theory of random network for oxide glasses. So what you see here is a very simple substance. This is silica, and silica is the sand that we all know of. On the right is the crystalline form of silica. It has this nice arrangement of silica tetrahedra. So all the black atoms that you see are silicon atoms, and all the white atoms are oxygen atoms. Okay. So what is known is silica forms these tetrahedral networks. Sort of this network architecture is what gives its rigidity and the strength. But what you see on the left is again a silica network. So this network is formed basically from the silicon atom and the oxygen atom intercalating with all its neighboring silica tetrahedron. So each unit that you see here is a tetrahedron, and all these tetrahedra link up together to form a strong rigid network. So what you see here is silica can exist both as a network in a crystalline state on the right and a completely glassy state on the left. So this led Zachariasen to propose his now very famous random network theory, which later on came out to be very true in predicting the structure. All right, so we talked a bit about how do you generate a glass, right? But from the physics perspective, the most important question that's still hotly debated is what exactly is the glass transition, okay? So traditional thermodynamics will tell you that if you have a liquid at a very high temperature, so the x-axis here is the temperature, and the y-axis here measures the volume of the substance, okay? So you heat up a material, it doesn't matter what the starting structure is. Once you heat it up sufficiently high, you form a liquid substance. And then once you cool it say you cool it slowly, then what thermodynamics tells you is there is a transition point that's denoted as Tm, which happens to be the melting point, where there is a sudden decrease in the volume, or alternatively, there's an increase in the density. So just from equilibrium perspective, the liquid gets transformed to a crystal. So this crystal has a lower volume, it has a lower energy, and is more stable than the liquid. But what's very interesting is, if you take the same liquid, but then instead of cooling it very slowly in an equilibrium process, if you cool it very rapidly and supercool it, meaning you cool it below the melting point, it so happens that you can preserve the glass structure, or in other words, the liquid structure. And it forms this new metastable phase that's called a glass. Okay? So what's very important to note is glass is not an equilibrium structure. So when you talk about phase diagrams, for instance, when you talk about crystals and liquids and where they are stable and so on, it's not appropriate to consider glass in the same figure, because these are structures that are formed from rapidly non-equilibrium processes. Okay, so what you see here is this vague definition of a temperature that's called Tg, and Tg is what we call the glass transition temperature, and this is the temperature below which all the atoms are basically frozen, and we say that glass is configurationally frozen, meaning these atoms cannot really display any long-term dynamics, and they cannot move. Okay, so there are several conflicting theories of glass transition, but what we know is qualitatively glass transition can be broken down into a few simple rules. Okay? So the first thing is the temperature upon which the molecular motions become active or inactive. That is really characterized by Tg. So what I mean by that? So if you take a glass from the low temperature and start heating up gradually, you increase the temperature. Okay? You will encounter the Tg, the glass transition, above which the atoms now have sufficient energy because they are at sufficiently high temperatures, and they start exhibiting rapidly evolving atomic motions. And essentially, they get transitioned to a liquid state. So Tg basically governs where the atomic motion is arrested. So is it a liquid or is it a glass, right? That's what Tg demarcates. So an alternate picture is that when you cool a liquid, of course, rapidly enough so that you follow this non-equilibrium protocol, and you cool it below Tg, what we do is we completely arrest the molecular motions, and this leads to glass basically behaving like a solid, and the viscosity increases by leaps and bounds, and it becomes fantastically large. It becomes about 10 power 12 Pascal seconds. So compare that to a liquid that has a very low viscosity, maybe of the order of a few Pascal seconds. Okay? And what's also very interesting is the glass transition temperature is highly material specific. It depends on what are the atomic species that are present in the material, what's the molecular weight of the material. For instance, if we talk about polymers, then a polymer that's very short versus a polymer that's very long have drastically different glass transition temperatures. And what's more interesting is this temperature Tg is not actually well defined. It is a function of how fast you cool the glass. So cooling the glass faster can give rise to glass transition temperature that's quite different from cooling it slower. So these are some physics that have perplexed scientists for long, but there are some understanding that's developed from several years of research in this field. And finally, when talking about the glass transition and glass transition physics, what's very interesting is a used glass can actually recrystallize and form a crystal. So this is very evident in laboratory equipment where you say have a glass vial or a glass beaker, and then you leave it unattended for some time, or maybe use it for a sufficiently long time. Based on some thermal fluctuations, the glass can become devitrified. A part of it can basically crystallize, and of course that loses its transparency. The crystal diffracts light, and it behaves as an opaque solid. So this is a very nice illustration way back in 1913. This appeared in the Popular Science magazine that shows both these regions, the glass on the left and a somewhat intermediate regime in the center, and a fully crystallized material on the right. Okay, so with that in mind, the next logical question that anyone could ask is, are there any restrictions on the materials that can form glasses? Okay. Can any material form a glass? So we'll begin with the traditional glasses that showed widespread use. So these are the network glasses that I briefly mentioned. These are made of silica tetrahedra, silicon in the center and oxygen on the three sides. And there are several such network glass formers that I've listed here. So borosilicate and pyrex are some of the examples. And of course, they found varied use in laboratory equipments and whatnot. Okay. So some of you might be curious to see if there are other materials that form glasses as well. And the answer is yes. There's a plethora of materials that form glasses and exhibit the same phenomena of glass transition that we just discussed. Polymers, for instance. So polymers, as you know, are any long chain molecules. So typically they are organic molecules with some additional linking agents. So one such polymer is shown here. This is polycarbonate. That's become ubiquitous in modern day use. So polycarbonate can be used in various forms, right? So these are some UV heat shield materials. The common plastic cup or plastic glass that we know is made of polycarbonate, as well as fancy eyewear. Okay, so all these are actually glasses. So all polymers, if you can imagine, given a sufficient processing, a suitable processing condition, can form glasses. Glasses are not just restricted to long molecules, but even small molecules like simple sugars that I've shown here, sorbitol. So what people are now proposing is, take these small molecules, you make them in a glassy state, and these can be used to deliver drugs that otherwise crystalline substances cannot deliver. So if you can process the crystal and reprocess it to form a glass, then you can essentially use it for very interesting medical applications. Okay. And of course, I was surprised to see that ice is a very interesting material. So water, as we know, it forms a crystal that is ice at 0 degrees Celsius, and of course you heat it and it forms a vapor. But I was personally very surprised to see that there are so many non-equilibrium states, meaning amorphous gases, that can be formed by cooling water or putting it under various extreme conditions like pressure and temperature. And some of these are highlighted here. So it forms what's called a low density amorphous phase, a very high density amorphous phase, a high density amorphous phase, and so on. So all these are very interesting physics problems where, based on some non-equilibrium processing, you can get a host of glasses from water, which we know has a very high propensity to form a crystal when it's cooled below its melting point. But the trick here is you need to cool it fast enough or subject it to some suitable non-equilibrium process. So by looking at all these examples that I've highlighted here, we can safely say that any material can theoretically form a glass. Okay? So it doesn't matter if it's a very complex molecule or a very simple atomic metal, it can form a glass under the right conditions. And these conditions are non-equilibrium conditions at sufficiently large cooling rates or suitably other possible processing conditions. So if you look at what are some of the basic rules for glass formation, this field has seen a lot of empirical rules that were developed, and quite often these are very material specific. So these rules are used for optimizing what possible glass formers could evolve based on research that people have done. So the first example, or the first rule that I would like to highlight, is this interatomic interactions between the elements. So they play a very crucial role in determining how easy it is to process a certain material as a glass. Okay? So these atomic elements or these atomic entities should have a very low propensity for forming a crystal and a very high propensity for forming a glass. So interatomic interactions are very crucial. And if you look at the number of elements in the glass, right? So it's easy to imagine that, say you have two scenarios, one of which is a single element. Naturally, all the atoms are of the same type. And the other is a very complex material where you have, say, 10 different elements, each with individual atomic sizes. There's a large difference between the size of these atoms. So one can clearly see that, or at least one can visualize that, it's much more difficult to form a crystal for the complex alloy that we have, right? If it's a single atom that's cooled from the liquid state, or single element that's cooled from the liquid state to the glassy state, it's very easy to form bonds between various atoms, right? All of them are alike, and this leads to a crystal formation. Whereas more the number of elements and larger the difference in atomic size, this easily enhances the glass formation ability. And this has been routinely employed by glass researchers to explore ever novel compositions that form glasses. The other very interesting phenomenon that we need to know is what's the cooling rate that you need to employ to form these glasses. Again, this is highly material specific. Note that what we just discussed is you need to cool this liquid phase at a very rapid time scale, meaning you need to quench it really fast. And there exists what's called a critical cooling rate for all these materials to form glasses. And if you take a look at the numbers that I've shown here, silica, we know, is a very good glass former that just requires a cooling rate of about 10 power minus 6 Celsius per second. So that's a very gentle cooling rate. You can basically melt silica, take it to its molten state, and then leave it in air, right? And it's very difficult to form a crystal out of it, and it will easily form a glass, a silica glass. Whereas if you go down the scale, water, right? Water, as we know, if you can cool water at this exceptionally high cooling rate of 10 power 7 degrees Celsius per second, then it's possible to form an ice out of it. Any lesser, it will form what's called a crystal, a hexagonal crystal water, crystal ice. Okay, and in that respect, if you talk about metals like silver, again, right? So these are individual atom types. So all the silver atoms are alike. So naturally forming a glass from silver is going to be a much tougher ordeal compared to a complex alloy like we just discussed. So naturally this requires a very large cooling rate of the order of 10 power 9 to 10 power 10 Celsius per second, degrees Celsius per second. And these are possible from various advancement over the last few years. I'll highlight these in the subsequent slides. Okay, so that's a brief intro to what are glasses, a bird's eye view of all the complex physics that takes place in glasses. Of course, each of these topics is an involved one that might require a separate lecture, but that's just a small bird's eye view. Okay, so let's look at some of the fascinating properties that glasses exhibit. Okay, so what we've seen is glass is one of the most used materials, and it does show a lot of diverse properties, and that naturally leads to a lot of diverse applications. So when we talk about material science in general, what we see is there are several factors that will basically influence how a material is eventually used. Okay. So what you see on the right is called the materials tetrahedron, for those who are not familiar to material science topics. So this is a tetrahedron that has interdependencies between what the structure of the material is, what is the processing that one employs to tune this material for a particular need, what are the properties of these materials, and essentially what's the performance of this material. So performance meaning, for instance, you want to use a very high strength material. How does it perform, right? So all these four factors are interdependent, and influencing one will definitely have an impact on all the other properties. And what's also interesting to see here is, of late, people have started talking about characterization, meaning how do you actually quantify or visualize these structures. Right? So there are several experimental techniques that I'll come to in a minute, but characterization forms another paradigm which will basically help us in engineering these properties. Okay. So let's take a look at the properties that glasses exhibit. So the first property that's readily witnessed by glass forming materials is viscosity. Okay, so it's the clearest physical indicator of a glass structure. So to give a brief overview of what viscosity is a property that measures the resistance of a material to deformation or flow. Okay? And it turns out that it's highly sensitive to temperature. And of course, viscosity of different materials are different, as we know. Water is something that has very low viscosity. Honey is something that has a very high viscosity. Right? So I thought it's a very interesting video to show. Sudipto, you can tell me if you're able to see the video.
Yeah, I think.
So I don't know how many of you are aware of this video, but this video has the distinction of being the longest continuously performed experiment. And it's been going on for about, I think, 100 years or so. And you can see that there is a drop of liquid that's falling. But the time scale, if you take a look, I know it's hard to see, but this experiment is a time lapse of about 3 years or so. Okay. And this is the famous pitch drop experiment. So pitch is a very gooey substance like tar that has a very high viscosity, and it takes a very long time for flowing, but eventually it does flow. Okay, and that effect is captured by the elegant Newton's law of viscosity that relates what's the shear stress on a substance, in this case the fluid, as a function of its property mu, that's a material constant that we call as the viscosity, and what's the deformation gradient that we impose on this. Okay. Now, why is this relevant for glasses? So glasses, as we know, is an intermediate substance. It's a metastable substance between a liquid and a solid. It behaves both like a liquid and as a solid. All that matters is what's the time scale at which you're looking at this atomic motion. Okay. So the graph on the right shows the evolution of viscosity on the y-axis as a function of inverse temperature on the x-axis. So this is 1 over T for all practical purposes. And what you can see is, as the temperature decreases, that is, we move from left to right, these glasses show a very, very strong scaling in terms of viscosity. So this is in log scale. You can see that there are about 15 orders of magnitude change in the viscosity upon increasing the temperature from 0 to essentially Tg. So an x-axis of 1 means that you're heating the substance up to the glass transition. Okay, so in other words, when you're cooling this material, that is, you're moving from left to right, right? The temperatures decreasing from left to right. You see that the viscosity essentially shows either very strong scaling, what are called strong glasses, or a very weak scaling, that's called a fragile glass. Okay? And we won't go into the physics of why such glasses show these behavior, but it suffices to know that viscosity is a very, very sensitive parameter that depends on the temperature. So again, this goes back to what we described in terms of atomic motion in glass. When you're at a very low temperature, somewhere over here on the top right corner, the viscosity is fantastically large. It's about 10 power 12 pascal second. So essentially that means that the glass doesn't flow and it behaves like a solid. But the moment you start heating up, the viscosity starts dropping, and at sufficiently large temperatures, you will encounter glass that starts to flow. And that's what viscosity captures. So moving on, the most important property that's important for performance point of view is what are the mechanical properties of glass. And here, some of these parameters I'll describe. They are very material science specific parameters. So what do we mean by strength? What do we mean by ductility? And what do we mean by toughness? Okay. So glass, as we know, is something that's very brittle. And that's got to do with the glass structure that I'll come to in a minute. But essentially, brittle materials show a behavior that's shown by the red curve in this graph. Okay. So what we're plotting is the variation in stress of a material as a function of strain or the deformation that you impose on the material. So a brittle material like glass basically does not show a large amount of extension. It just catastrophically fails or breaks at some particular strain line. That's what the red curve shows. Okay? And what's a ductile material? So ductile material, metals for instance, polymers, another very good example, are something that show an initial elastic response and followed by a very long or very large plastic deformation regime. Okay? And the area that's under this curve, under the stress strain curve, is proportional or equal to the amount of energy that's absorbed during this deformation. And that is what we mean by toughness. So glasses are something when non-processed, when not processed with all the techniques that I'll come to in a minute, they are very brittle. Okay? Whereas metals are ductile. And the reason for that is the makeup in terms of the structure. So what we show on the top are atomic planes of a metal or a crystal, and crystals basically deform by what's called a dislocation mechanism. So there are planes of atoms that can slide past each other, and that allows the material to withstand a much larger load in the plastic regime. These can be this material can be pulled for much larger strains than glasses. So glasses, as we see in the bottom set of figures, they form what's called a shear transformation zone. So what we see is a small region here that's highlighted in red. So these small localized regions in glass will undergo some sort of deformation at a very local scale. Okay? And these will basically expand and communicate with its neighbors. And this will basically lead to a catastrophic failure. So if you have a pre-existing defect in a glass, this defect can essentially grow, and that's what leads to the brittle nature of glass. And what's very interesting is these shear transformation zones, which are small regions of small atomistically minute regions in the glass, they form small displacements. So all these atoms within the displacement zone essentially get transformed, and these grow in size and form what's called shear bands. So once the shear bands grow, this leads to catastrophic failure. So in this, at this juncture, I just wanted to show you a simulation that was done in our group by Ranga, one of the MTech students. So he took a glass structure. So this is a glass structure that's made of several elements. It's a multi-component glass structure. And what simulations allow us to visualize is how do these shear transformation zones essentially progress. Okay? So this is the undeformed structure. And what we're doing is we're applying a tensile force on the top and the bottom. We're basically pulling it along the vertical axis. And what we are showing by color coding is how much strain develops in the material at a very, very local scale. Okay? So all these sizes that you're seeing is of the order of a few nanometers. So you can see that strain starts to get localized in some of these regions, and these are clear indicators of all these shear transformation zones that I just talked about. And what happens as you progressively pull on the material, the shear transformation zone grows and eventually leads to a catastrophic failure. So that's the entire essence of deformation in glasses. Now, this is quite not true. Yeah. So that was the traditional drawback of glasses, in that it cannot withstand a large amount of stress and it breaks catastrophically. Now, what happened was there was a large research group that was led by Professor Dues and co-workers in Caltech back in 1960s that they came up with this fascinating class of glasses called bulk metallic glasses. So essentially what this means, you add a lot of different metallic elements, and what we've seen is the more complex the structure, or the chemical entities that make up the structure, the easier it is to form this glass. And I'd like to show this plot that compares what's the fracture toughness on the y-axis as a function of yield strength for various classes of materials. What you see here on the bottom left are traditional polymers that have a very low yield strength and a very low fracture toughness. Whereas all these violet bubbles that you see, these are engineering metals that have a very large fracture toughness, but modestly large yield strength. Okay. What we see on the bottom right are traditional glasses. So glasses, as we know, have a very high strength. They can withstand a very high strength, but the drawback is that they're not tough. They are brittle and they break very easily. So what Duez and co-workers came up with is to basically amalgamate the strength of metals and the strength of glasses. So they engineered novel metals that are made up of these metallic elements, so one of which is listed here. So this is a glass that's made up of palladium, silver, phosphorus, silicon, and germanium in a certain composition. And these form metallic glasses which show simultaneously high fracture toughness and high yield strength. Okay. So this is spawned off a very huge active area of research. People come up with novel compositions for these bulk metallic glasses, various processing techniques for making very large bulk metallic glasses and so on. So much so that there's a registered trademark company called Liquid Metal. Some of you might be aware of this. So they've started using these bulk metallic glasses in almost everything under the sun. So some of these are shown here. So these are golf heads that make use of liquid metals. They can synthesize these in much larger quantities now. And they started putting it in all sorts of products, bicycles, sporting goods, even medical equipments. So some of these are biocompatible, meaning now you can engineer a very precise glass instrument or a glass medical device that you can use for biomedical applications. Okay. So the third important property that I wanted to highlight is what is the nature of dynamics in these glass structures. So what we've just seen is glass is configurationally frozen below the glass transition temperature, meaning all the atoms are frozen in place. But that does not mean that it doesn't show dynamics. So dynamics, what we mean by dynamics is small vibrations of atoms, and these could be of the order of a few nanometers as well as you increase the temperature. So glass demonstrates a very rich spectrum of dynamics. So what I show here on this graph here is some of these atomic displacements, what we call as relaxations, as a function of the frequency at which they undergo these deformations. So the alpha peak that we see is the traditional glass transition that takes of the order of a few tenths of seconds maybe. On the other hand, if you keep it, I'm sorry, this figure is cut. I'm not able to see the x-axis values here. But essentially what we're doing is we're trying to probe what are the dynamics in glasses as a function of the time scale at which these dynamics happen. Okay. I think the better picture would be okay. So the boson peak, for instance, is a very interesting fluctuation in the glass dynamics, and this happens at the order of terahertz frequencies, so 10 power minus 12 seconds. So that's the very rapid motion that the glass atoms exhibit, and this go all the way to very, very low frequencies of the order of maybe 10 power minus 5 hertz or so, and these are the alpha relaxations that we know of, and that's the glass transition that we are familiar with. So these dynamical events, they do happen, but at a very short length and time scale, right? And they're very hard to see at the naked eye. And people long thought that glasses will actually flow with time. They are essentially like liquids, and given enough time, they should actually flow, right, and demonstrate a behavior that's more suitable of glasses. And in fact, for a very long time, people thought that the glasses, the stained glasses that were used in construction, in churches and so on, had this very unique bulge towards the bottom of the panel. And people thought that that was because of glass that's flowing with time. So these church glass walls might be maybe a few hundred years old, and people thought that that was enough for glass to flow and show a very liquid-like behavior. But it turns out that that's not really true. That was an engineering problem. People did not cut the glass flat enough. And for glass to actually flow and demonstrate a behavior like a liquid, it might take, you know, fantastically large times, maybe of the order of 10 power 20, 10 power 30 seconds or so. It might exceed the age of the universe. And that goes on to show that glasses are quite stable in some sense, although they are actually metastable. Okay. And the dynamics, the nature of dynamics is still very hotly debated. And there are several properties and processing capabilities that depend on these dynamics shown in glasses. Okay. So I'll quickly go through some of these processing protocols that people came up with to enhance the structure of glasses and get superior properties out of it. As we know, the traditional method for glass synthesis involves a routine melting of the raw materials and then cooling it in a very controlled manner. So these are some traditional glass blowing illustrations that many of us might be familiar with. Of course, you can place a mold, and that can allow us to shape the glass in a particular form. And what was also technologically very important is what's called the float glass process. And what essentially we do is we take the raw materials, heat it up in a furnace, and then pass it through molten tin. Okay? And this molten tin is very crucial because that forms a very nice layer over which the glass can be rolled into flat sheets. And this allowed the process to generate a very large volume of sheet glass that was used in construction. Now, modern glass forming, as we know, began with these processes, but there was a lot of research and technological innovations that went into forming these glasses. And processing these glasses is one of the important properties for enhancing the, the functionality of the glass. Okay, so we go back to the materials tetrahedron where I showed that processing forms one of the important legs for optimizing the glass property. And what we know is there's a lot of techniques for strengthening of glasses, and that's achieved by several means. I just wanted to highlight one particular means here, and that is by inducing compressive stresses in a glass. Okay, so what happens is when you induce a compressive stress, the glass essentially does not break. Any particular deformation that you impose on the glass is resisted by the compressive stresses in the material. I think this is a very nice illustration to show. Again, I'm not sure how many people have seen this, but it's a nice video.
Hey, it's me, Destin. Welcome back to Smarter Every Day. Today we're going to do awesome science.
I'll go to the interesting part. So what we do is, so what we're going to see is a piece of glass that's dipped into a liquid, okay, molten glass dipped into a liquid, and it forms what's called a Prince Rupert tail. Okay, so this person was a Prince Rupert, and we'll see why this glass is very interesting.
Of the tail, technically it wasn't the of the tail that makes it go. But technically it wasn't the hair that broke. So if you look closely, you can see that.
Okay, what you saw there was a glass structure that had a lot of compressive stress at the head. Okay, and this is a very thin tail that the glass structure has, and this tail is essentially under a lot of tensile stress. And it turns out that tensile stresses are very bad for strength of the glass. And when the hammer actually impinges on the head, it does not break from the head. In fact, what happens is the stresses get transferred through the tail, and the tail eventually breaks first, and then the glass subsequently shatters. So this is a very important property that can be obtained by sufficient thermal processing. In fact, it's called tempering, that makes compressive stresses as the go-to method for increasing the strength of glass. And quite routinely, we can make glasses that are about 5 times stronger than traditional annealed glasses. And there are several other synthesis routes that I wanted to briefly mention. The method that we know is the traditional method that we know is rapidly cooling a liquid, but there are several other possible technologies that we can use for getting these high-tech glasses. What's very interesting is you can deposit a small set of vapor of this liquid on a substrate, and this is called vapor deposition. And this was used very successfully by Corning and several other companies for creating glasses with superior strength that were used in optical fibers, in cellular devices, and so on. Some of these other techniques are also listed here. Just skip them for want of time. Okay. I wanted to briefly talk about some of the advances that we've seen in glass science and glass technology. It's definitely true that we've come a very long way over the last few decades. Right? Forget the jump from prehistoric times to the modern times, but even if we take just the last couple of decades, there's been tremendous improvements in several properties and processing techniques that these glasses, the glass field has seen. Okay, and the first example that I wanted to highlight is the amount of sophistication that has gone behind in characterizing these materials. So what we see here is the X-ray diffraction peak for a glass film and the bulk glass structure, and this has basically enabled us to rapidly characterize what's the short range order in glass and so on. And what you see on the figure on the right is a differential scanning calorimetry that looks something like this. So this basically heats up a material at a particular rate, and it can precisely capture what's the change in dynamics that happens when the glass transition occurs. So for this particular glass, the glass transition temperature is about it's close to 800 degrees, 800 Kelvin, and this can be captured very routinely by using some of these devices. But perhaps the most interesting characterization tool is the employing of high-resolution electronic microscopy. So the pictures that you see on the bottom panel are very high-resolution images of a glass, where you can see the individual arrangement of these atomic units. So all these are representative of the short-range order, but you can clearly see the lack of long-range order in these structures. So these machines are quite indispensable, and they've become routinely used. They're starting to find novel applications every day. There are novel materials that are developed with each passing day, and these are quite indispensable. The second advancement is, of course, with the processing and the synthesis. We just saw that glasses typically require a very high cooling rate, especially if they are very simple materials. And if you just take a look at this numbers in the table, you can see that there's a fantastically large variation in the cooling rate that's possible, going from about 10 degrees Celsius per second all the way up to 10 power 14 degrees Celsius per second. So these are some of the cooling rates that are routinely achieved by using these sophisticated processing techniques. And what this has allowed? This has allowed us to synthesize very specialized glasses that have far superior properties compared to anything that was seen maybe a couple of decades ago. And there are several optimization that people do in terms of the chemical modification, what are the heat treatments and surface treatments that are possible. And the scale of glass research is becoming quite unprecedented. And finally, the advancement that I am more passionate about is the amount of theory and simulations that have gone behind understanding these materials, these fascinating materials. So I won't go into the technical details, but there are literally a ton, literally tons of theories that talk about how glasses are formed, what happens at the nanoscale. For instance, people talk about what is the arrangement of atoms between a normal liquid and a supercooled liquid, which is the precursor to forming a glass. And people do see that there are several interesting factors. So there is the short scale ordering in supercooled liquids that you can see by the blue spheres. So these are small pockets of the glassy liquid that have displaced a very large amount of distance compared to a normal liquid. So these form pockets of regions in space that show enhanced dynamics. And there are several theories. For instance, the mode coupling theory is able to predict what's the relaxation time of a particular glass. Based on some structural parameters, it can differentiate what's the time scale for a glass to be formed versus a supercooled liquid and a normal liquid. What I'm directly involved in is trying to use simulations for studying these fundamental processing relations. I won't go into too much details, but what is now routinely done is we can describe all the forces of interaction between all the elements that form the glass. Okay? So these are some illustrations that I wanted to show. What you see here is a silica glass. You can see the silicon and oxygen atoms shown by red and yellow. And what people have studied here is how does a void form in this glass and how does it propagate as a function of deformation. And this is a small representative image, but now people can study what happens when a billion such atoms are there in the glass, right? So these are unprecedented scales that people study these glass phenomena in. Okay, so I think I'm almost out of time. So what I wanted to conclude is, we've definitely come a very long way from using natural glasses such as obsidian way back in the Stone Age, and there is clearly a very great synergistic development of various fields that I've shown here. One is the incredible engineering advances that researchers have come up with in terms of processing, in terms of choosing the materials that form the glass, and in terms of putting them to all these high-tech applications. On the other hand, there's a lot of advancement in the fundamental understanding for controlling how glasses can be formed. And of course, this has been largely driven by all these cutting-edge applications, the need for innovation at every step. Right? We want stronger glasses, more functional glasses, and now's the time that the demand has been at the peak. And all these individual factors have led to development of the glass technology. And now it's no wonder that it's more than $100 billion industry with all these companies that are pioneered glass forming. So yeah, so with this, I wanted to leave you with this question. So glasses definitely, literally are super cool materials. They are cool below the glass transition, but based on all the other factors that I have discussed, this is the answer that I want you to seek. Are in glasses super cool materials? Okay. Yeah. Thank you, everyone.